So today we'll have a brief overview on the basic properties of stars to start off with, and then we will look at classification of stellar spectra. Okay, and a lot of you would be familiar with many of the basic concepts, but if I'm going too fast, then please don't hesitate to stop. Let me start off by asking you the question of what do you understand by a star? What is a star? Any one of you can unmute and say.
Star is a sphere of hot gas whose pressure and temperature at its core undergoes nuclear fusion, and giving it the energy to not collapse under its own gravity.
Okay. Rest of you agree with it? Ahan also was trying to unmute himself.
Yes, I think Aquino pretty much nailed what I was going to say.
Okay, excellent. Okay. This is just a definition or a quote which I took from a Sky Telescope article, which effectively covers what Aquino said and Ahan was about to say. A star is a luminous ball of gas, mostly hydrogen and helium, held together by its own gravity. Nuclear fusion reactions in its core support the star against gravity and produce photons and heat, as well as many small amounts of heavier elements. Okay. Now, you'll also know that, as you mentioned, that the energy generation process is nuclear reactions in the central regions of the star, where the temperature is high enough for nuclear reactions to take place. More massive the star is, the higher would be the temperature inside, and you would be able to synthesize heavier elements. Heavier elements, because what happens in the center is that you have to overcome the Coulombic forces of repulsion, right? When you're trying to combine two protons, and you know that the proton and proton will have Coulombic repulsion, which varies as 1 upon r squared. And as long as when you bring it closer and closer, then the Coulombic forces are going to get stronger and stronger, right? And so to overcome the Coulombic forces, you need the high energies of the particles so that quantum mechanically it is able to tunnel through the barrier and get within a distance where the strong nuclear forces come into play, which will bind protons together to form, in this case, the helium nucleus. But in the case of heavier atoms or heavier nuclei, then it'll combine, less heavy nuclei will combine to form more heavy nuclei, right? And the repulsive forces would be more if you're not considering protons, but nuclei with many more protons. So you need higher temperatures to synthesize elements with higher atomic number or atomic mass, and the temperatures will be higher for more massive stars. You know, in a star like our sun, most of the reactions which take place are through the proton-proton chain, where protons combine to form helium nucleus, right? Now, let me ask you another question, that if protons are combining to form a helium nucleus, why don't all the protons combine and be done with it? Why does it keep doing it so slowly that the sun in the main sequence itself, right, is there for about 5 billion years or so? Why doesn't it all combine together and go bang, and here it is? Just a physical understanding of why.
It's because of Pauli's exclusion principle, right? There's so many protons and they can't all come close enough together at once. So like it has to happen bit by bit.
Not quite, actually. No, that is not quite the right answer. Pauli's exclusion principle will come into play when you're trying to get into degenerate states. Here, actually, for all practical purposes, we can consider it as an ideal fluid over there, ideal gas, and the pressure would be given by NKT. There would be a component of radiation pressure as well. The radiation pressure, as you would sort of expect, gets more important for more massive stars. But stars like our sun, gas pressure is a major component. Any question? Any other suggestions? Okay, you can think about it this way. Okay, for example, I mentioned about getting through the Coulombic barrier by tunneling through it. Tunneling is a quantum mechanical concept, and that is why you may not have done that, and that is why you're struggling. But the probability or the chances of getting through it is larger when the energy of the particles are higher. So whatever distribution of energies you take as an ideal gas, it will have a Maxwell-Boltzmann distribution, and it is only the high energy particles that has a higher probability of getting through. But also you notice that when you look at a distribution, probability keeps increasing with energy, but the number of particles of high energy also goes down, right? So there is a region where the probability of combining increases, and that is referred to as a gamma window. For the MSc students, we'll do that in slightly more detail. But over here, I think, conceptually, it is adequate to realize that the probability of, being able to penetrate the Coulombic barrier, and after which the strong nuclear forces take over, is significant for only the higher energy particles in the energy distribution of the protons inside the star. And those protons are few in number because of the Maxwell-Boltzmann distribution. The higher the energies you go, the number of particles will keep decreasing. And it's a balance between these two, that fusion keeps occurring at a small rate. The other thing also, if you remember, the time scales of interaction, right, which we mentioned, the cross-section of interactions, that will also determine how slowly the sun burns. For example, if the cross-sections are low, then the sun would keep burning for a long period of time. And if you look at, if you remember the PP chain, the proton-proton chain, the first reaction in the proton-proton chain was the slowest, right? And that also affects, that is another way of looking at it, affects the fact that the sun keeps shining for billions of years. Now, we'll just have a look at the gross overall properties of stars. First is the mass range, okay? We look at what is the smallest mass, what is the largest mass, and what is it that we call a star, okay? First, we look at the low end of the mass distribution, and stars, gas clouds which collapse and are not able to sustain nuclear reactions, like proton-proton chain in the center of the sun, they don't become a star, and these objects are referred to as brown dwarfs. Okay, so understanding the boundary between the stellar and the substellar boundary, what is not a star and what is a star, that is something which is still often hotly debated, because when somebody says that, I found a star which is a star, and it is of very low mass, we'll see what those numbers are, then there would be sort of questions as to whether it is really a star or is it not a star. Are nuclear reactions going on in the center? So so that kind of work is largely, model dependent or theoretical understanding of the way stars evolve and the way brown dwarfs or substellar objects evolve. What do objects close to either side of the stellar-substellar boundary look like to an observer? What are the masses and other structural parameters of objects on either side of the stellar-substellar boundary? And how are they related? How are the different parameters related? So you need both theoretical models as well as observations to try and sort it out, and then hold your heart to your hand and say, hey, I do believe that this to be a low mass star, or I believe this to be a brown dwarf or a substellar object. Now, as you all correctly pointed out, that for it to be a star, hydrogen burning or that would have to be there, sustained nuclear reactions. That is what we call a star. Now you can see over here that these are different models, okay? Different models which have been constructed by different groups, and this sort of goes on for over a decade or so. Results are summarized over here, which I took from a paper by Dietrich in 2014. And you can see they're generally in the ballpark of about 0.07 solar masses, okay? 0.07 solar masses, which is heavier than Jupiter. But this is sort of the lower limit at what theory tells us. And the precise value also would depend upon what are the properties that you assign to it. For example, for it to collapse, you need to actually cool the star, right? As it collapses, internal heat would be generated, but you need to get rid of the heat. Now, for example, if you don't get rid of the heat, for example, one of the ways of getting rid of the heat is for the metals to actually radiate, absorb and re-radiate the heat out. So if it is metal-free, for example, you'll see that a slightly greater mass is required. And that is why in the early history of the universe, a population 3 stars from the primeval neutral hydrogen form without metals, you'd have to form more massive stars than what you would do if you had metals in them. So we will not worry about the details over here. This is just to give you an overview that this is about 0.07 is at the lower end of the mass of a star if it were to be called a star at all. Now, Dietrich et al. Claimed this object, 2 mass J0523-1403, which, as you can see, is a small fraction of the solar luminosity. It's about 8.6% of the radius of the sun, and it's about 67 times the mass of Jupiter, which is about 0.064 times the mass of the sun. And they looked at various relationships, for example, the radius luminosity relationship being one of them, and radius effective temperature, and try to argue that, based on the location of this object and the evolutionary tracks that they looked at, that this is likely to be a star, and this is amongst the lowest mass stars that have been detected. Objects over here, in this range over here, are largely brown dwarfs, including this Kelu 1AB. And you can see that within the errors, although it's 0.064, that within the errors of 0.012, it is consistent with the theoretical models of about 0.07 being the lowest mass that you can have for a star, which is roughly about 70 times the mass of Jupiter. Okay. Now then you can ask yourself, what is the high end? How high can it get? Okay. This is the Tarantula Nebula. Tarantula Nebula, also called 30 Doradus in the Large Magellanic Cloud. And there's a very rich cluster of massive stars called R136. And this is an image on the right, which is taken of the R136 cluster with the very large telescope, the VLT telescope of the European Southern Observatory. This has been taken at an infrared wavelength of 2.2 microns so that you can get through the dust and see all the stars. And there is a clutch of supermassive stars, out of which R136A1 is the highest. Okay. And how high is it? It is among the most massive stars known. They plotted this in a Hertzsprung-Russell diagram. So currently it is believed to be about 250 solar masses. Okay, 250 solar masses. So that is at the high end of the mass distribution. Okay, you will find that when you look up Wikipedia of massive stars, you'll find a long list over there. But many of them are contested, some more seriously than others. And these high mass stars also have very strong winds. So it is believed that from the models they have made that it would have started off at about 300 solar masses. And these winds are, because of their high luminosity, they would also have strong radiation pressure. And if it was much more massive than that, and as we mentioned, and the limit set by the Eddington luminosity would actually just blow the star apart. The temperature is about 46,000 Kelvin. So roughly in the ballpark about 50,000 Kelvin. So the only thing I must warn you over there is that because these massive stars, this one is not, is based on theoretical understanding of where it lies on a Hertzsprung-Russell diagram and the modeling of the structural parameters. It is not a direct measurement of the mass of the object as you would do in a binary system as we learned. And it is, you can see, is nearly 10 to the power of 7 times more luminous than the sun. Okay, not quite 10 to the power of 7, but it is getting there. And the effective radius is about 40 times the radius of the sun. Okay, 40 our sun. But we've seen that in giants, actually, the radii can be much larger. But in terms of luminosity, these are, and mass, these are amongst the at the higher end of the distribution. Now, this is another very rich cluster, compact cluster of stars. This is in our Milky Way itself, NGC 3603, and that's towards the Carina Nebula. And this one is an eclipsing binary with a period of 3.77 days. So you can see that with an eclipsing binary, from the dynamics of the star, as we talked about when we were discussing measurement of masses of stars, from the parameters of the binary system, and given that's an eclipsing binary, you can assume it to be close orbit, the perpendicularity orbit being in the sky plane, so that you're seeing it edgeways. And the estimates of the mass are 116 and 89 solar masses. Okay, and given the fact that these high mass stars have very strong stellar winds, the initial mass is for these two stars in an eclipsing binary system has been estimated to be 150 and 106 solar masses. And as we say, these high mass stars are not going to live long. It will be on million-year time scales kind of thing is what they would survive, what they would live. So this is just rounding numbers off a little bit. So these are the two stars in the binary system, both about 1.5 million years is 2.5 into 10 to the power of 6 times luminous, 1.5 into 10 to the power of 6 times luminous as the sun. And you can see it's close to about 30 times the radius of the sun. Age is estimated to be 1.5 billion years. So this is the kind of regime of high mass stars. And you want to keep exploring that to try and find out, understand cellular evolution models, understand the mass range. And that primarily relates to how stars are forming. Now, I've shown you an example of a very low mass star and examples of very high mass stars. But what does the distribution look like? That is given by what is called the initial mass function. Initial mass function basically tells you the mass function when stars formed, not the current star formation, for example, in a distant of our galaxy. Because why not? Because if you look at the masses of stars in a disk of our galaxy, and the most massive stars would have exploded as supernovae. So you'll not get a correct representation of the initial mass function. Initial mass function gives a mass distribution for the stars immediately after the stars have formed. So IMF is intimately related to the star formation processes. And Salpeter in 1955 described it for stars in the solar neighborhood in our galaxy. And so that is referred to as the Salpeter mass function. But there are obviously challenges in determining mass because the most accurate measurements we saw come from binary stellar systems. So in this particular case, when you want to calculate IMF, you'd have to convert luminosities to, or absolute magnitudes to mass by knowing the masses of stars in binary systems, knowing what their luminosities are, and try to establish a mass-luminosity relationship, and then you calculate the masses of these objects. So there is a well-defined mass-luminosity relationship. Schematically, it is shown over here, which I again picked up from the Georgia State University site. The slopes vary depending upon what mass range or luminosity range you're talking about. So you convert luminosity or absolute magnitude to mass, calculated by observing binary systems. And as I mentioned, slope varies in different degrees, but roughly it is in the ballpark of 3 to 4, except at the lower end, actually it is even goes below 3. Okay, so you can see that luminosity increases for bulk of the objects in approximately as about 3.5. So if your mass doubles, your luminosity would go up by a factor of 2 to the power of 3.5. So luminosity increases very rapidly with mass. So this is basically an empirical relationship, which you have a theoretical understanding as well. This particular figure is from a paper, a little old, Massey and Mayer. It was from the Encyclopedia of Astronomy and Astrophysics. And this actually gives you a slightly more detailed and a schematic illustration from the Georgia State University site, which I picked up. And they pick up different regions with different slopes. Okay, and More luminous stars also have shorter lifetimes, as we say, because they burn up the fuel much faster. So if you're examining the IMF in an old cluster, you may not see any of the massive stars. Okay, but that does not imply that massive stars do not form. It is just that the massive stars evolved. So you have to be conscious of these aspects when you're trying to calculate the IMF, because as we shall see in a short while, that the massive stars are not only very few in number, but they also live very short periods. So you have a double disadvantage in trying to determine the mass function or for the very massive stars. The other aspects which you have to bear in mind for the massive stars is mass loss from stars, because massive stars lose mass much more than less massive stars, as we just saw when we were talking about the most massive stars. To get the IMF, one needs to take into account as well. So it is reasonably well defined between about half a solar mass and 50 solar masses. But at the low end, we have difficulties in determining masses in binary systems as well and calibrating it well. At the high mass end, there are too few of them. And also distant galaxies, it has been a bit of a challenge, just observational constraints. Now for a solar neighborhood, you can define Xi m, which is Xi m dm is the number of stars between mass m and dm. So this is just the number of stars at Xi m. And this is given by, in the solar neighborhood, by m to the power of minus 2.35, where Xi 0 is a constant which sets the local stellar density. This should have been width and not width. Okay? But I can also find out from this equation, can be integrated to combine, to determine the number of stars between masses M1 and M2. So if I want to determine the number of stars between masses M1 and M2, I need to integrate this expression between M1 and M2. And this is just a simple integration over here. And these are the limits M1 to M2. And once I know Xi 0 from calibration of the local stars in the local solar density, then I can go and determine the number of stars. Similarly, I can also determine a number of total mass in stars with masses between M1 and M2 by multiplying this by M, Xi m by M. So it gives me the total mass of the stars between M1 and M2. This gives me the total number. This gives me the total mass. This is what the expression Xi m looks like when you derive it. Most of the mass, as you can see, are in low mass stars, right? This is a log scale, okay? This has been expressed in units of solar masses. But I think all I need you to take home is that it is approximately given by a slope of minus 2.35. There are many more stars, low mass stars, than high mass stars. But if there is a period of intense star formation, then the luminosity could be dominated by the high mass stars because they are extremely luminous, but they also have short lifetimes. So when you look at any stellar population today, you will even find less of the high mass stars than what the initial mass function tells you, because they would have evolved away. Salpeter's power law cannot be extrapolated to very low masses. One thing, of course, we integrate to zero mass is going to diverge, but there is also evidence from work by a number of authors that this does tend to flatten at low masses. So if you take between about 0.5 to about 50 solar masses or so, that you're reasonably okay with this m to the power of minus 2.35. Okay. There are slight deviations from it, but that gives you a reasonable description of the distribution of masses of stars. So remember that there are many more stars as of low mass stars, and these low mass stars also evolve much more slowly, right? Because our sun will remains in the main sequence for about 5 billion years and then evolves to a white dwarf in another 5 billion years. So you can see that it's a pretty long time scale compared to the millions of years when we talked about for the most massive stars, which we met earlier today. Now, the initial mass function is interesting to ask oneself, where does it originate? What is the origin of the IMF? Why do stars form stars this way? A lot of work has been done, but there is no uniform consensus that this is what it is. Dense cores of molecular clouds have a similar distribution, but one has to do more work to try and see how well this is related to the IMF. The other question is the IMF the same everywhere? We have only been able to explore in some depth with in the Magellanic Clouds, which are very close by to us, the small Magellanic Cloud and the large Magellanic Cloud, the SMC and the LMC, and the Milky Way. And you can see that it is, I mean, there are variations within a sample, within a galaxy as well. But you can see if you take an average value, it is close to the saltpeter value of 2.35. Okay, and in principle, it should change with cosmic epoch if stars formed without less of metals or no metals at all, then you would form more massive stars, as we mentioned a little while earlier. Briefly again, what are the masses of stellar remnants? A star like our sun would end up as a white dwarf. Stars 8 or 9 times more massive than our sun would end up as a neutron star. And stars much more massive, maybe 20, 25 times the mass of our sun, would end up as a black hole, right? These precise numbers are, these are just ballpark numbers that I'm giving you. You can see if I look at the white dwarfs, they are about 0.6 solar masses or so. Here you can see the median or mean value is about 0.621, which is the median mass of a white dwarf. This is just for you to be familiar with the numbers. And you can see that 1.44 is the maximum mass of a white dwarf star, which is the Chandrasekhar mass limit, because there are no nuclear reactions going on in a white dwarf. It is largely supported by the electron degeneracy pressure, and that is where the Pauli exclusion principle comes in, and you cannot pack it for more than that, and that sets a limit which Chandrasekhar worked out. Okay, for the MSc class we will derive that, but for the introductory course it is beyond our scope right now. And if you look at neutron stars, okay, neutron stars, there seems to be slight difference in masses depending upon whether the neutron star is in a white dwarf binary companion or a neutron star companion. And these have been estimated from binary systems, so they're reasonably sort of accurate. And you can see it's in the ballpark of 1.55, 1.33. And the largest, one of the largest masses, I don't know if this has been exceeded or not. This was reported in 2020, that is last year, of 2.14 solar masses. Okay, 2.14 solar masses. And it is important to try and determine that, because the maximum mass that a neutron star can have also depends on the equation of state of the neutron star. Okay, equation of state of a neutron star. So if you have massive stars, then you can rule out certain equations of state of the neutron star itself. Okay, so remember that white dwarf, the median value is about 0.6 solar masses, and the maximum mass is 1.4 solar masses. Neutron stars typically, the maximum mass that's been detected so far is about 2 solar masses. The median values are about 1.3, 1.5. So you can take it as about roughly 1.4 solar masses. Black holes, I'm talking over here of just stellar remnants, okay? We have supermassive black holes as we saw in the center of our own galaxy and other galaxies. But in the case of black holes, in the low mass black hole binary systems, where matter from a companion goes on to the black hole or is accreted by the black hole by overflowing the Roche lobe, those are in the range of, you can see, about 10 solar masses or so, whereas high mass black hole systems where the companion actually has a strong stellar wind, okay, and strong stellar wind, and the black hole accretes material from the stellar wind fed by winds from the massive stellar companion. There you can see also the black hole masses tend to be larger. So we look at a few other physical parameters. What are the sizes of stars? We've spent quite some time while in our discussions on measurements of physical quantities on the measurements of stars. So I will not get into the techniques of measuring, but just briefly overview the results. In this Hertzsprung-Russell diagram, as we saw, there would be outliers, the most massive one and the least massive ones. But roughly you can see that it sort of varies by about 7 orders of magnitude. Luminosity, Temperature varies by more than an order of magnitude. Even 1500 to 40,000 or so is what we met, so about 30 times. And radii of most stars about 2 orders of magnitude. But this again, most stars, I'm pressing on the most over here because this is the range I'm considering in the main sequence. But you'll notice that when we talked about giants, they will be much bigger than this 10 solar radii, which is drawn on this figure. And these lines essentially come from the Stefan Boltzmann's law that it varies as r squared over here. Okay, the luminosity would vary as the square of the radius. For example, over here you can see it's 0.01 for 0.1, and if you increase the radius by a factor of 10, then the luminosity should go up by a factor of 100, and that is what you find over here, 0.01 to solar luminosity. Similarly, from 1 to 100, when you go from 1 to 10. Okay, so these are just sort of lines which are given over here to illustrate to you the effect of the radius. So when you measure, this was also given as an assignment. So when you measure the sizes, this is just a catalog which was published quite some time ago in 2000. Okay, this is the 3rd edition. They have kept catalog of apparent diameters and absolute radii of stars measured by different means, including interferometer means. And this is in terms of solar diameters. Okay, most of it is around 1 solar radius, and it tapers off as you go to larger radii. But one has to be careful that this dip over here is probably due to selection effects, because smaller stars, it will be more difficult to determine their diameters, particularly with interferometric means. Let's look at some of the stars we have met, just to give you a brief overview. This is Sirius A and Sirius B. I want you to realize the difference between these two images on the right. On the upper one is an HST image. The lower one is a Chandra image of the same stellar system. The scales are different. Ignore these spikes over here. They are artifacts of the images. But what you see over here in the optical, this is Sirius B, which is a white dwarf star, and this is Sirius A, which is a main sequence star. Okay. This is the X-ray image of it. The white dwarf is very hot, and so it radiates much more copiously in the X-ray region of the spectrum than Sirius A, which is a main sequence star. Sirius B has a temperature of about 25,000 Kelvin compared to Sirius A, which has a temperature of 9,900 or close to 10,000 Kelvin. Okay. But Sirius B, although it is very luminous, its radius is extremely small. Okay. Radius is extremely small, and that is why the luminosity is very low. Okay. L is equal to 4 pi r squared t to the power of 4. Although t is high, extremely small radius makes it less luminous. And the mass is also, white dwarf mass is about a solar mass in this case, whereas Sirius A is about 2 times the mass of the sun. Because it is heavier than the sun, the central temperature is also larger. And here the carbon-nitrogen-oxygen cycle for generating nuclear power, because of the higher temperature, makes a more important contribution. It's a binary system with a period of 50.1 years and a separation of 20 astronomical units. Okay. Now let's go and look at some of the sizes of the giants and the supergiants. Okay. Here I've just given you a list. Don't worry too much about the details. That this relates to the opacity of the cloud, but just take it as a radius of the star for our purposes. So you can see that the largest stars go up to about 1,500 times the radius of the sun. Okay, the others are 1,700, 1,400. So roughly about 1,000 to 1,400, 1,500 times, 1,700 times the radius of the sun. And compare this with the compact objects, for example, 10 to 20 kilometers for neutron stars, and white dwarfs typically of a few thousand kilometers or so. Now, just to summarize what we have done so far, there are outliers, but I'm just giving you a broad summary of where most stars lie. And on the top line is the mass of the star, of the sun, and then the mass range over here. Okay? 0.06 to about 200. 0.06 or 0.07 that you can, decide. Luminosity is 4 × 10⁻33 Earths per second, about 1,000 times less luminous to about 1,000,000 times more luminous. Radius, again, this is the radius of the sun, 0.08 times the radius of the sun to about 1,500 times the radius of the sun. Effective temperature of the sun is about close to 6,000 degrees Kelvin, and we have met the low luminosity or the small stars with about 1,500 Kelvin, and the high mass stars about 50,000 Kelvin. So this gives you a range of the physical properties of the sun. You can also look at other parameters such as average density and surface gravity. I just want to stress that in the main sequence, there is a relatively small range of mean densities. It's still relatively small compared to the giants and the supergiants. The sun is about 1.41 grams per centimeter cubed, as you're familiar with. Water, as you all know, is about 1 gram per centimeter cubed. Actually, we humans also, the average density is close to this, about 1 gram per centimeter cubed. When you take an O5 star, you'll see what an O5 star later this morning. That's one of the more massive stars, larger in size, density is low. When you get an M-type star, which is more compact, less luminous, it is about 5 grams per centimeter cubed. But when you take the giants and the supergiants, okay, they're extremely less tenuous. Giants about 10 to the power of minus 7 grams per centimeter cubed. Supergiants about 10 to the power of minus 9 grams per centimeter cubed. And compared to this, white dwarfs are about 10 to the power of 5, which are the remnants of stars like our sun. Neutron stars, which are the remnants of stars which are 9 to 10 times more massive than the sun. And you can see that this is even more dense than the average nuclear density. Okay. And just to remind you again, at sea level, density of water is 1 gram per centimeter cubed, and air is about 0.001 gram per centimeter cubed. So an O5 star is slightly denser than the air at the sea level, but on the other hand, giants and supergiants, they're extremely tenuous, but yet they're held together by their gravity. And the central densities are much higher. For the sun, it's about 150 grams per centimeter cubed. And for the range of stars, it lies between about 10 and 1,000 grams per centimeter cubed. So you should realize that it's much denser at the center compared to what is at the surface. And the Hertzsprung-Russell diagrams, which is a key tool in understanding stars and stellar evolution. You see a broad range of parameters. Temperatures are given here. This and absolute magnitude or luminosity in terms of the solar luminosity over here. And similarly for the Hertzsprung-Russell diagram on the right as well. And this is from the Hipparchus data, which has about 22,000 stars and about 10,000 low luminosity dwarfs from the Gliese catalog of natural nearby stars, which have been put in. And this is Gaia data, which is about 4 million stars within about 5,000 light years from the sun. So you can see that the Hertzsprung-Russell diagrams are well established with very large numbers of stars now. And you can see the broad patterns very clearly in both the figures over here. And they give you the range of parameters on average. But as we saw that there could be more extreme values, people are always on the lookout to try and understand the least massive star or the most massive star and see what constraints they might put on our understanding of stars. The last one I wanted to deal with briefly about overall properties is surface gravity. Surface gravity, as you know, is gm upon r squared. You would have calculated this for the Earth. For anybody, you can calculate it. And in the photospheres of stars, which consist of gas, pressure is equal to nkt. Now, what happens is that the emission lines, the width of the emission lines is going to vary with surface gravity, as well as the temperature over there, isn't it? Because when material is moving about with higher velocities, then you will get broader lines than if they're moving about with lower velocities. And that is what is shown over here. The surface gravity plays an important role. This particular figure has picked up stars of the same temperature so that one can isolate the effects of surface gravity, and those with higher surface gravity, that means the pressure is increasing downwards, where there is high surface gravity, you can see clearly that there are broader lines. So from the line widths, one can also try and understand the surfaces of stars and as well as the atmospheres. Main sequence stars have higher surface gravity than the giants, because giants, they blow up to very large sizes, right? So when R is very large, the surface gravity drops. Whereas white dwarfs and neutron stars, their masses of the solar masses or a couple of solar masses, but you can see they're very compact, right? So surface gravity is large for white dwarfs and neutron stars. Just a few examples of G. From the Earth, you know that log G, this is in CGS units, 980 centimeter per second squared, and log G, if you take, that is the way it is usually written, is 2.992. And this is for the sun. You can see that the sun, the surface gravity is much more than on the Earth. But when you take a giant star like Betelgeuse, log G is of the order of minus 0.6. So it is much smaller than that of the sun, right? And similarly for Sirius B, which is a white dwarf, if you actually do the sums, you'll get log G is equal to 8, right? Which is 10 to the power of 8. And this one I've just shown you to introduce you to a brown dwarf, okay, which is Gliese 229b. Mass is about 0.03 times the solar mass.
G here is surface gravity?
G here is surface gravity, that's right. Okay. Surface gravity, but taken the log of the value. For example, G is equal to gm upon r squared, as we just saw a little while ago, okay, gm upon r squared. And after calculating the value, we've taken the log, and the numbers which are quoted here are the log of the value, right? Okay, just bear it in mind. So G is the surface gravity. Okay, and over here you can see the density is high. These are compact objects, and log G is about approximately 5. So this is another physical parameter which plays an important role in our understanding of stars. I will just show you a simple way to calculate the average temperature and pressure within a star, and then we will have a look at stellar spectra. Average temperature within a star, we'll just express it as T average, and let's say the star of mass m star has n particles, okay? Then the total thermal energy, because you know it is half kT and 3/2 kT is per particle, you multiply that by n, so you get the total thermal energy in the star, okay? 3/2 k T average into n. Now for our simplicity, we'll assume that the star is entirely made of hydrogen, which is ionized. So there are two particles, proton and an electron. So the mean molecular weight, therefore, is mu is equal to 1/2. So the number of particles would be given by 2 into m star divided by mh. mh is the mass of the proton. So the total thermal energy now, I'm going to substitute for n over here. Okay, the 2 cancels out. Total thermal energy is given by 3k T average m star, mass of the star, multiplied by the mass of the hydrogen atom, which is the mass of the proton. Now we know that the gravitational energy of a star, approximately, you can have some factors over here, it doesn't matter, gm squared upon r. You're just doing an order of magnitude calculation. Combining the two equations, okay, by using the virial theorem, we have not derived it, but we have stated it, that twice the kinetic energy, in this case the thermal energy, plus the potential energy is equal to 0. So using that, I will equate these two, the gravitational potential energy over here of the star and the total thermal energy of the star over here. Equating these two, I can get a value for the average temperature. Okay, and that gives me a temperature of about 4 million degrees Kelvin. And it's not too bad, because the surface temperature we know is about 5,800 degrees Kelvin, and the interior temperature close to where the nuclear reactions are taking place is about 16 million degrees Kelvin. So at least a very rough back of the envelope calculation will give you from the mass and the radius of the star what the average temperature within the star is. For the main sequence stars, it varies between 1 million degrees Kelvin and about 100 million degrees Kelvin or so. Okay? And this interior temperature is the one which is relevant for the nuclear reactions to take place. We can also calculate very easily the surface, the central pressure of a star. This is again a rough calculation because we won't have occasion to look at the equations of stellar structure in detail with the IDSS students. So I thought I would just give you simple ways of calculating two physical quantities in the interior of a star. Suppose I consider a spherical shell, okay? Spherical shell over here. Then the mass within any of these shells would be given by 4 pi r squared dr, that would be the volume. 4 pi r squared is the circumference multiplied by dr would give it a volume. And if you multiply by the average density within the shell, okay, density within the shell rho r, that will give you the mass within the shell, okay? This is effectively an expression of the conservation of mass as well, which is one of the equations of stellar structure. You can see that radius decreases, but dmr increases with radius, okay? As the volume of the spherical shell increases as the square of the radius, okay? And recall that surface gravity is equal to gm upon r squared. And in any case, in any situation where the star is in hydrostatic equilibrium, you'll have to balance the pressure due to the gas with the thermal pressure that is supporting it. Thermal, in the case of high mass stars, radiation pressure will also play an important role. Now, this equation of hydrostatic balance, I've just stated it over here. You may have derived it in some other mechanics classes as well. The dpr dr is given by the variation of rho r minus rho r gr. Gr is the surface gravity. Okay, I can express this as dpr dr is equal to minus rho r gr, and I can substitute for rho r as well as gr from these two equations. And if I do that, I will get this expression of dpr. It's a very simple thing. You can do it yourself after I circulate these PDF files with you. So this is the equation we get by just substituting expressions for rho r and gr in the equation of hydrostatic balance. Now I will integrate this expression from the surface to the center of the star. Pressure at the surface is 0 and is maximum at the center. Pc is the central pressure. P0 is equal to 0 at the surface. And whereas the mass is the 0 at the surface and maximum, 0 at the center and maximum at the surface, right? It encloses all the mass at the surface. So if I redo this equation, because this will give me Pc, then I take out G upon 4 pi. I just put m star over here, which will cancel out. And I integrate this from 0 to m star. The star, sorry, came at the wrong place. M upon r to the power of 4Tm. So this expression is nothing but the average value of mr upon r to the power of 4. So I can crudely express this as m star upon r to the power of 4, which will give me an expression for the central pressure. So if I do this very rough calculation, I get about 10 to the power of 15 dynes per centimeter squared. And for detailed modeling of the stellar interior, you'll get about 2 times 10 to the power of, for the sun, 2 times 10 to the power of 17 dynes per centimeter squared. So at least it gives me an idea of how high the pressure is in the central regions of the stars. This beautiful book by Chandrasekhar, published way back in 1939, An Introduction to the Study of Stellar Structure, begins with a lot of nice theorems and lemmas to estimate, get a rough estimate or get an estimate of limits or measurements of parameters of the interiors of stars. For those of you who are interested a bit more, I would suggest that you have a look at this book. It is available, I think in 1939, there are PDF files available for free in the internet as well. So try and have a look at that. So what we have looked at today, and this first part, is the gross overall important physical parameters of stars and because these play an important role in understanding stellar evolution, and in a way to estimate or get a rough estimate of a couple of physical parameters within the stars themselves as well. We've also looked at measurements of some of these physical parameters for mass in the more extremes of low mass stars, which just barely has become a star, and the highest, most massive stars, which are going to evolve very rapidly in a time scale of millions of years to end up as supernovae and ejecting most of the material into outer space, from which the next generations of stars will form. We have looked at radius, we have looked at surface gravity, and these are some of the important physical parameters. And I've also listed for you the luminosities and temperatures, and you're all very familiar with the Hertzsprung-Russell diagram, which plots luminosity versus temperature, and which plays an extremely critical role in trying to understand how stars evolve. And that is one of the holy grails in astronomy and astrophysics, because evolution of galaxies themselves are governed by the evolution of the population of stellar populations, which are residing in these galaxies. And even when galaxies collide, you have a copious amount of star formation. And how do these stars evolve? How do these merged components or interacting components evolve? These are all interesting questions which you will learn much more if you pursue the subject. The other important aspect is the star formation history of the universe itself. Star formation actually peaked at a redshift of about 2. Why did it happen so? That rate of star formation is much higher than what we find today in a nearby universe, for example. So these are all aspects which I'm sure you will keep reading and studying as you go on, even at a popular level if you don't take up astronomy and astrophysics, because these are fundamental towards understanding of our universe.